This is Mildred Dresselhaus. Today, at the very end of the session, I will be giving a talk on enhancing Raman signals. So the concept there is to have some kind of enhancement mechanism that's complementary to what is done on an electron microscope. Well, it's always a great pleasure to come to the UK and to attend a conference in a field that you know very little about. So when I was told about a possible award in the field of microscopy, I was kind of shocked because I don't really work in this field. And or at least I don't think I contribute that much to the field. But somebody thought I might have done. So I tried to make some contact between what I have done and what people are interested in here. So to me, microscopy allows you to see things that are really small, and you could see them in great detail. Spectroscopy is very similar. You don't look at exactly the same things, so you get complementary information. But complementary information always allows you to understand what you're looking at with another technique better. So I thought maybe something like that might be appropriate for speaking here. So my talk is enhancing signals from the nanoworld, and I think that's kind of what you're interested in. So let me just start a bit and what it is that I've been doing all these years. So let's see, this one advances. So I actually was a student here before this chart in the 1950s. I was in the UK. I was at Newnham College at Cambridge, so that precedes this. But I didn't know anything about carbon at that time, and I didn't even know I was going to be in condensed matter physics, so that's really too soon. But I started my independent career in 1960, and at that time, I was kind of motivated to do something different than my colleagues. It's always nice to work on something that you don't have a whole lot of pressure on you to produce every day. At that time, my family started, and I had 4 children right at the beginning of that curve. And I thought it would be impossible for me to compete with society. So I picked some very obscure topic like carbon research. And you could see from this view graph, there weren't a whole lot of people that were interested. The plot here is the number of papers published per year. So there were essentially none, measure very small. And a good fraction of those were produced by our group. So. And it was of the order of 2 or 3 per year, like that. Production of papers was much smaller at that time. We didn't have all the resources that you have nowadays. So no computers, nothing like that. So, okay. So the early years, I was studying graphite because we didn't even understand what happens when you have an ordered structure of carbon. So that was the first decade. And then in the 1970s, I moved to trying to study individual layers, but I didn't know how to do them, so I'll tell you a little bit about how we managed to do that, and that was the intercalation compounds. And then 1985, of course, there was fullerenes came along, and I had to join that crowd, and then nanotubes and everything else, and that's what I'm going to tell you about pretty much today. In my talk. Okay, so just that. So the original inspiration of doing something different came from this picture. So the electronic structure of carbon systems is different from everything else. You know, at that time, we didn't really know that everything else was different about a single layer of a carbon system. Maybe a single layer of anything is just the dimensionality makes it different. So anyway, I was very much motivated by this, and the idea that I could really contribute something to the field was that at that time, two things happened. Lasers came in 1960, and and I said, well, let's do something with lasers. And well, lasers were real big things with glass and gases, and it was very different from what you know today. But that's what we used. And the earliest work that we did was done with a homemade laser. You couldn't buy anything. And so I'll tell you all about that. So it'll be a little interesting for you from a historical. We had a lot of history here at this conference, so I have a little bit of history. So we had magnetic fields at Cambridge in the U.S., and so I thought that would be a good thing to work with. And the laser just came on, and this is the very first experiment was done with a laser in a magnetic field. And it was kind of an interesting experiment for me anyway. We used the magnetic field and circularly polarized light to be able to distinguish the spin associated with a carbon atom. And we were interested in doing this to identify where in reciprocal space the electrons and holes were located in carbon. At that time, we thought that it was known, but what was known was opposite to what we know today. And this is the experiment that established where the holes and electrons were, and it was done with a laser, and it was done with a magnetic field. But we didn't have a microscope in this one. But it was kind of a high-resolution experiment. And so the bottom line of what you see here is that, so we're plotting here the change in reflectivity of electrons coming off a carbon surface. We're making transitions between two different electronic states. And if the electrons and holes would be symmetric, then the peaks would look the same when you're going up a quantum number or down the same quantum number, because we were going from 4 to 1, 4 to 5, or 5 to 4. So if they're symmetric, then you get the same answer. But you see, they're not symmetric. They don't occur quite in the same frequency, and they don't have the same line shape and all that. So we knew that the electrons and holes could be distinguished, and then we figured out which one was which by the direction of the circularly polarized light. So this is the first laser experiment, kind of an interesting thing. So this is work done in the 1960s. But I was always interested in doing single layer, but we didn't know how to make samples. So we had many things at this conference about making special samples to do specific microscopy experiments. Well, this kind of high resolution is also like that. So the idea here was to take a single layer of carbon, but we didn't know how to make a single layer. We peeled graphite all the time, but we couldn't make one layer. And we couldn't, even if we made one layer, we wouldn't know that we had one layer. So that was kind of difficult. So we did this by intercalation compounds, and that was known at that time already that you can introduce molecules. Well, this is alkali metals here, but we also did molecules. We did all kinds of things. And then we could study individual layers of things between, so that separated the carbon layers. So that was work that we did in the 1970s. A review article was written of a decade's work in 1981. So this told us that this was interesting thing to do, and we got transport properties, optical properties, magnetic properties, and many other things, and during that decade. So it was a lot of fun. Just at that time, we had the first conference. See, in those days, we didn't have international conferences. Nowadays, it's very easy to go across the ocean, come from Asia, come from North America, any place, get together. But in those days, this was very rare. So this guy wrote the paper in 1960, and we were doing something in 1960. So this is Hans-Peter Böhm, and he was working in Heidelberg in Germany, and he was doing very much related work. He did single layers of graphene, but nobody really knew much about this paper until many years later. And I met him in 1977. That's 17 years after this. We met each other, and we never discussed this. We were only discussing intercalation compounds. So this gives you sort of an idea that not only were we not working on science wasn't the way it is today, but we didn't even think about our own work the way we think about it today. So it's a kind of different era. I think it's important to recognize that, especially when we sign the book and we think back of the history of this society, which predates this work. Okay, so now I'm moving into what's happening in the 1980s, so one decade at a time. So in 1985, fullerenes were discovered. The history of the discovery of fullerenes was working on clusters, because we didn't know how big the clusters could be. So I was involved with the early work on the clusters. And so I remember going up to Exxon Laboratory. At that time, we had research labs that did very serious science. This is a thing of the past. We had Bell Labs, we had Exxon, different places. And so these people had gone up to clusters as up to 15. But we did an experiment by having a laser impinge on a carbon surface, and we could tell by how much material, how much energy went into the system. So, and we could also tell how many atoms came off. So we didn't have enough. If C2, C3 up to C15 came off, it wasn't enough to remove all the atoms. So we knew that there were bigger clusters that came off all at once. That was it, but we didn't have any idea what size. And so for me, the big, wonderful thing of the Smalley work and Kroto, there were different people involved with the discovery of the C60 and this big peak. So this is a big thing of the 1980s for me. And so at that time, so we're still in the 1980s, and I had another interest. I got into carbon fibers through intercalation compounds because I wanted to measure something that we could make smaller and smaller and smaller, because a fiber, I thought maybe could be made into just like a multi-wall nanotube, but I didn't have an idea of the exactly multi-wall nanotube at the time. But we were working on this in the 1980s before the nanotubes were discovered. But nanotubes actually were known in the 1970s and even in the 1950s, but people didn't know that they were known. There were papers published, but they weren't publicized, shall we say. So, okay, so now what happened that in this history that was important, at least in my career, is I was working on this problem here with the carbon fibers, So carbon fibers is something like very big multi-wall tubes, big ones. And Smalley was working on this stuff, C60, and somebody asked us the question, what's the connection between your work and his work? And so, well, we came up with this crazy idea that maybe you could we knew you could make C70, but so we knew C60 and C70. And the rest was just extrapolation in the mind. So, okay, the pretty crazy idea, but it turned out to be not too crazy because somebody then asked me a question. You know, in science, people ask you questions, and when you don't know the answer, you start doing some new experiments. And so that led to suppose that you could make a nanotube. Would it be worth all the effort? Because we didn't know, of course, how to make a nanotube. But would it be an interesting thing to have and to study? So that's the experiment we did. Would it be interesting? So I had two visitors, Fujita and Saito, two young people. Young people are always smart and energetic and willing to do crazy things. And they showed up, and I said, suppose we can make a nanotube. What would it be like? Would it be interesting? And so we came up with this idea that a nanotube would have very few atoms around it, and therefore be a low-dimensional system. So we would have to have quantized states. So if you take graphene, here's graphene. Everybody knows graphene nowadays. You have this cones that are connected. But we don't have all these states possible. We only have a few states. So if we have 10 atoms, we have 10 states. So we can have only 10 cutting lines. And therefore, the cutting line either goes to the apex or it doesn't. If it doesn't go through the apex, it could only be a semiconductor. There's no way to connect the carriers in these states, the electrons you put in. So this gave us the idea of the semiconducting metallicity of carbon nanotubes. If you could ever make this would be really interesting because we'd have a system that either could be metallic or semiconducting, depending on how the atoms were placed around the cylinder. You know, we call that chirality today. So anyway, that was a prediction, and it predicted these high-density states. So what does this have to do with microscopy? Well, what it really has to do with microscopy is that we have a singularity in the density of states. So we're creating something that has a huge enhancement of signal. So what my talk is about is signals that get enhanced. You do it with a microscope, and we do it with different particles. So this is now electron states. But then I'm going to talk about doing it with phonon states, and I'm going to talk about doing it with a mixture of electron phonons and the electron-phonon interaction. So that's my inspiration came for what to talk about today. So that's what the subject matter is. Well, we have the nanotubes, so we decided to do some spectroscopy and see what the vibrations are like. And this is the first experiment, and this is Peter Eklund. He had a graduate student, Rao, who is well known, probably many people in this room, but this is his thesis topic. And so we varied the laser excitation energy. That's a normal thing to do nowadays. That time it wasn't so common to do that sort of thing. But you see the spectrum is very, very different every time you change the excitation energy. In Raman spectroscopy, the results should be the same with the excitation. That's only a transition to a virtual state. Doesn't have to be a real state. But here we have something that changes. That means that we have something happening that's specific to that state. So we have a big amplification at certain energies. So we have a resonant process. And the intensity of these peaks were many orders of magnitude. Great, so this is like the microscope again. the peak intensity was many orders of magnitude more than it should have been if it wasn't resonant. So in fact, we had the idea, so this is 1997 or so, this paper, this one here, left-hand side. This, on the right-hand side, is done a couple of years later. We had the idea, if the signal is so great, instead of doing this with a whole bunch of nanotubes, let's just take one nanotube. Can we get a spectrum? If you have a big enhancement factor of thousands, or maybe more than that, 10,000. So we tried one nanotube. And look at this, you get a spectrum here from just one nanotube. So, so this is like microscopy, very large enhancement, when you have some phenomenon that gives you multiplication. In a microscope, you have the optics, the mechanism that makes the microscope do the enhancement. Here we have the physics of the situation. We bring together states that are very heavily concentrated. And maybe this gives you an idea of putting together the amplification of physics with the application of the microscope. And that's a little bit what I'm going to be talking later on in my, toward the end of my talk. Okay, so now a little bit on graphene. We had to have graphene. Manchester is known for graphene, so this is the right place to talk about graphene. So we have a monolayer graphene here on the left, and bilayer. And they look almost the same when you do the density of states over the whole Brouillon zone. But if you just look at the K point, where most people talk about, this is linear E versus K, and that's quadratic. So, and that's what the big excitement is, just because so much happens at just specific states in momentum space. And I think in the microscope, you do many experiments that are very limited also in K space for specific experiments. So I think there's some generality between this and this connection. So now we do E versus K. You see all the difference. We move away from the K point. They're very different. But right at the K point, they're all the same. And because of this difference, we get this extremely unusual situation that almost never happens in physics, where the higher order terms are bigger than the first order terms. First order perturbation theory in Raman spectra should give you, oops, I'm doing the wrong thing here. Let me get back. I don't know how to do back. Yeah, okay, now we're back. So the first order process, so this is the two carbon atoms just going like that. So that's first order process. The second order process is huge. Second order perturbation theory should be just a perturbation on this, it should be tiny. So that, but it's just the opposite. And it has to do with the fact that we have this linear E versus K. And so this is, again, going back to the microscope story, that every transition is allowed. Everything is resonant. I showed you that Raman spectra and nanotubes can be seen even on the individual level, one tube, and it's tiny. It's less than 1 nanometer in the diameter. So we're looking at something really tiny, and but we see a very big signal from just one tube. And it has to do with every single state being resonant. So that you get this big multiplication factor like you do with a microscope. So now, this is now the second order process we can do. So what happens in a second order process? You take a photon comes in, electron gets excited. The second order process, we go from K to K prime. But K and K prime have all the same energies. They just have time reversal spin symmetry. So in K space, they're different. So you can make this transition, and it's the whole length of the Brouillon zone. But then we come back, and then we recombine. And that gives features that are very easy to see in the spectrum. So here's one with blue light, green light, red light, so it's dispersive. And if we do it in second order, we get all these different lines. So we have many things in the spectra to look at and measure. So high resolution. Another topic where we get big amplification. Here's a ribbon. A ribbon is very tiny. It's less than a nanometer or so across with 5 different rows of carbon atoms. Carbon-carbon distance nearest neighbor is 1.4 angstroms, so it's small number. And but yet, we get a big amplification of signal that you could see at the edge. Now I'm going to talk about edge states. I didn't hear about edge states today, but that's a really good topic for microscopy, I believe. So you have different edges with high symmetry. So this is zigzag edge, and this is armchair edge. And they're very different. They have different selection rules, so we can pick out which one we have, and they have differences in spectra. So they're very distinct when you look at them probably in an electron microscope. You see, I'll show you that as well. So we had well, this all started with an idea. Somebody came along and wanted to see density of states of electrons and carbon. So we did some density of states calculations. And we came up with this really remarkable result that for these zigzag edges that I showed you where they go boom like that, they look like a zigzag, you get this huge density of states right at the Fermi level. This is 0 energy, so Fermi level. And no matter how thick the ribbon is, any width, you always get that high density of states. So that's something going to be resonant. It's going to be large, big enhancement factor from the physics. So we can go look for that. And so we did Raman spectra, and you can distinguish when you're on an armchair edge and when you're on a zigzag edge. So this is done now with Raman, and here it is with a scanning probe method. You can see which edge you have, just atomic position. And this is with what the phonons are doing. And so the spectrum look different, and so we can tell which edge we're looking at. Another example that we did with ribbons. So I went to a conference, and somebody came up and asked me, I have this kind of sample. Is this interesting? So I said, I have no idea. Why don't you come up to MIT and spend some time? So this is somebody in Mexico. So we arranged, got a small grant, travel grant, and they came up and we looked at this now. We did both Raman and we did microscopy. But now I'm going to show you microscopy. So here we are, and here's, we have now pole pieces. And we have beam going, and so what happens? So here's a sample again, and so we're looking in the microscope. We were really astonished. If you put leads on the sample while you're looking in the microscope, and you put a current through it, and the current isn't very high, we put a couple of volts. But because the conductivity is so high, you heat up the sample locally, and we got this structure. And this is done on an ordinary microscope. There's no aberration correction or anything with this. This is just the student microscope in the practice lab. The students, what was used for that. And we got this spectrum. It's pretty amazing to us. We didn't expect that. So this is, again, amplification that comes about by changing the physics. When you heat this up, the carbon, we heard this in some of the other talks, the carbon atoms get very mobile, and they like to form layered structures with high symmetry, ground state. And so this is another example what you can do with microscopy in conjunction with other things. Now I have another few comments that I'm going to make about enhancing signals. There are many different ways of enhancing signals, and they're shown here. SWRS is something that's been known for a long, long time, and I was motivated by SWRS. I love SWRS because SWRS gives you not quantitative information, but it shows you what you can do. And it gives you an idea what you might look for when you do it quantitatively. I didn't hear a single talk on SWRS, but I think that would be something I would look, when I don't know when the experiment would work, you can do that easily and find out if you get a big signal, then you know it's possible, and then you really do the experiment. Okay, so this is the history of SWRS. It goes back to 1974, which is probably before many people in the audience were born. So this has been around for a long time. The problem with it is that it works on an electromagnetic effect, and it gives you a multiplication factor that's very, very large in signal. But as you move the little particle that's creating this big enhancement in the electromagnetic field, the multiplication factor changes dramatically. So you never get the same answer twice, but you know that there's a multiplication factor, and it could be large. So just knowing enhancement, even if it's not quantitative, could be very valuable. We didn't hear much about this here, and because microscopists really want to know everything precisely. But sometimes it's important to know if a phenomenon exists, and this is a good way to measure that. So I just offer that as a suggestion. There are two mechanisms. There's the electromagnetic one that's been studied for a long time, which has to do with the high dipole, well, it's not dipole, multipole effects that you can get if you have an irregular particle. You get all kinds of field components, derivatives of the field. And that's what the electromagnetic effect is about for SWRS. But very few people have looked at the chemical mechanism. It turns out that in graphene, you get a good chance to look at the chemical mechanism, and that's what I'm going to talk about for the rest of the time today. That such effect exists, Stephanie Reich gave a talk earlier this year that I heard that was very beautiful. And what she did, she put a carbon nanotube between two tiny gold particles and got a huge enhancement factor. It gives you an idea. And in the UK, I guess it's in Manchester, Shaden, he must be in Manchester. This is Manchester work. Belongs to, maybe he's in Cambridge, but connected with the early work in graphene. And so they did an experiment on SWRS. They got a big enhancement factor shown here as well in graphene. So graphene shows SWRS. One of the visitors coming to me, so her name is Shi Lin, and what she did, she put a piece of graphene, and it had some Scotch tape on it. You know, when you make a sample, you take it off graphite, and then you make a single sheet, and not all the contaminant was removed. We heard about contaminants earlier today from one of the speakers. The contaminants was very important in this experiment because the contaminants are seen over here. So pristine graphene will have a Raman spectrum that looks like this. But if you don't take off the Scotch tape carefully, clean it, you get all these other peaks. So that was very interesting. Where do all these peaks come from when you have graphene? And why are they so big? Because the contaminants shouldn't be as big as graphene itself. So this is very interesting. So what's happening? So this is the beginning of what we call the GERS effect. So surface-enhanced Raman, but this is graphene-enhanced Raman. So if you have these same kind of molecules, instead of they sitting on with these particles, like in SWRs, they get big enhancement, they're sitting on graphene, you get a similar kind of effect. Not as much multiplication, only maybe a factor of 10 or 100. But so now I'm going to just say what happens. So fluorescence doesn't occur in graphene because the fluorescence signal is damped very, very quickly, and then we could see what's left, which is the Raman enhancement effect. So that can be seen directly, and so here is a flask that has. We're comparing what happens if you have graphene or you don't have graphene. In the case of graphene, the fluorescence is killed right away. It acts, and then we can do the Raman experiment because the lifetime of the excited state in carbon and graphene is much longer than the fluorescence effect. So fluorescence effect disappears, so we can get rid of that. And so we can see these little particles sitting. You can see the spectrum of the Scotch tape on the graphene. And so here it is, the Raman enhancement effect that I'm talking about. Laser comes in, you have the molecules sitting, and you can get the spectrum of all the different molecules. Of course, if you do it a single molecule that you know exactly what you want, then you can get information. But this gives you the idea about doing the experiment. And then I'll show you some results on particular molecules that we use, like here, phthalocyanin. So, and what this shows is every place you have graphene, you get a big signal. Where you don't have graphene underneath, you don't get a signal. So that proves there's a correlation. That's what that's supposed to say. And what it says, this one says that the enhancement signal is large if you have a monolayer, but if you have few layers, like 2 or 3, then you still get a signal. But if you have many layers, like 10, you don't get anything. So 1 layer is the best, and so this GERS effect works with a single layer of graphene. So that's interesting. So we try to make a model for it. So we can have either a metallic or a semiconducting surface, and phonon comes in, hits the surface, and then a photon gets out, creates a phonon in the process, and we can measure what happens to the phonon. But things can happen in any order, and so that's what the theory is about. Then you do just second-order perturbation theory, simple like that, and but you can have different matrix elements depending on what the process is, as I've shown on the left. So that's basically what our model is, and when that happens, it shows that we could either add a phonon or subtract one, and we get an extra peak. And that's where the extra effect occurs relative to the laser energy. So the prediction is that plus or minus the phonon energy is where we should see the enhancement, and that's where we observe it experimentally. And we could observe it by changing laser excitation energy, so we get that peak moving in energy space. So that's what the most elementary explanation of the effect is that we have been studying in the last few months, and so this is current work. I always like to talk about something I've been doing recently, and it's an enhancement effect, and it's caused by molecules, so that's kind of appeals to anybody. So it's similar to GERS, but it's quantitative, and depending on how many molecules, it multiplies proportionately to the number of molecules. So we like it because it's more quantitative than it's similar to GERS, but it's a more quantitative system. And it has a polarization because we can, with annealing, we can make the molecules stand up if they're asymmetric and line up the pi bonds, and that gives it further enhancement. So we could see that effect, and that's shown here with the annealing, effect of annealing. Get more of this GERS effect than without it. And this is the last part of this. So if you have one layered compound that gives an enhancement effect, are there other layered compounds that give us an enhancement? And at this conference, we had people talking about graphene and then beyond graphene. So here we have some beyond graphene. So we had MOS2, and we've done a whole bunch of different dichalcogenides. Graphene works the best, but the other ones also show this enhancement factor. And, but not everything shows an enhancement factor. Only those things that have hexagons, so we have hexagons here, that's graphene. And MOS2 has sort of like hexagons. When you look at it from the C-axis down, they don't quite match the unit cell distance, but they are hexagonal. So graphene works better because we get the matching. But the others do have a similar symmetry, so we get some component. And we have a substrate that has no hexagons, no enhancement. So it has to have something that's like the molecule that's being attracted and multiplied. These signals multiply. And microscopy is sort of like that. Not everything makes a good sample. You have to have specific characteristics of your sample. So much effort that we heard about in the last couple of days is about sample preparation to match it to the technique that you have available. And it's the same thing with these kinds of materials. Wait, I want to go this way. So here are different substrates, and you can see graphene is the best. Boron nitride it's not conducting, but it's pretty good. So it has something to do with the symmetry more than it has to do with metallicity. And then on the bottom, we have silicon, SiO2. That doesn't do anything at all. So it doesn't match. It doesn't have hexagons. It doesn't match. So that's where we are with this project pretty much. And so there's some more of the substrates. And we can tell specific vibrations that are excited in the molecules if you put just a single molecule on them. That's what this thing shows. And some molecules give stronger interaction than others, and I said that the matching of the hexagons and the vibrations of graphene is valuable. So this is just the last slide, and the take-home message is we like enhancement. We learn about enhancement from microscopy. And I think we look in science, we look for other cases where effects get big because of something, and that tells us that we should study the science behind it. And so this is one example recently that I've gotten into, and I wanted to tell you something about it. And it's a very new open field, so I'm sure there are lots of ideas that you might have, and so good for graduate students to work in areas where there's not too much competition. So there's not much competition at the moment. So that's what I have for today, and willing to take a question or two if there's time.